All right, so this lecture is on lighting calculations, basically, in OpenGL, how we do them in the shaders, and what effect they have. So what we've done already is we've kind of taken the geometrical transformations of everything that we send in, made sure that everything is put in the correct place, everything is drawn in the correct location on the screen. Our three-dimensional images or three-dimensional coordinates are transformed in such a way that they end up in a normal place on the screen. It looks like we have kind of perspective projection, so everything looks correct. We have kind of correct distances. Things get smaller as they get further away, so on and so forth. And we can set up these transformation matrices to make sure that we can draw the same thing in different locations simply by changing the transformation that is applied, but drawing the same thing over and over again. So we have a lot of control over things, locations on the screen, how things look. But at this point, we want to start looking at the color in a little bit more detail. Rather than just calculating a single color and kind of putting it on the pixels that we have, we want to be able to set up calculations that take into account the position of a light, the intensity of a light, the position and material of an object. Is it more shiny? Is it less shiny? So on and so forth. Use this information to actually calculate the color for every single pixel that we end up kind of putting onto the screen, so that our image is, has proper three-dimensional, proper three dimension. When we look at it, that the effect that we get on the screen is not only that things are in the correct location, but they also are correctly lit. So we have an environmental factor that makes our three dimensions that much more realistic. So if we just look at kind of lights in general, lights in reality, we obviously have lights that are coming from the ceiling here, we have lights that are coming in from the window. All of these lights start as a kind of wave with some wavelength going in some direction. If that light hits something, either it gets absorbed, or part of it gets absorbed by whatever it hits, part of it gets reflected by whatever it hits. In some cases, it's reflected in many directions, and then we could take each of these kind of vectors or waves from then on, find out what it hits next, so on and so forth, until it hits the eye of myself, and then I see a color there. But the color that I see on a single point in kind of this actual real environment is kind of a function of light that has come from God knows where, or several lights that have come from all over the place, hit a bunch of different surfaces. Some of it been absorbed, some of it been reflected, and it ends up kind of in my eye as a mix of all of these things. And you can imagine how complex the calculations for this, to actually draw an environment like this room with all of you in it, calculating all of these different light sources in this way would be. So in order to simulate real light, we kind of split it into a couple of components. And we say, how can we take, in particular, the light that reflects off of, or kind of is distributed off of matte surfaces, which is called diffuse light, and kind of calculate that as a separate entity. Then take things that are actually reflected off of shiny surfaces and say, okay, if surfaces are shiny, I need to add another component of light and add that on top. Then I can say, in reality, we have a bunch of light that doesn't really directly hit a specific thing and then kind of get reflected into my eye. Instead, it kind of goes all over the place. It hits, hundreds of times different, like the walls on the different sides of this room, and just kind of ends up illuminating everything from every side. And instead of calculating all of that, we can say, can I just take the ambience of this room? Can I say, what is kind of the sum of all the light that just reflects all over the place, and set that up as a single ambient color of this room? So the window is on this side. So I'm getting a little bit more lit from this side. Even if I were to turn out the lights, I still wouldn't be completely unlit and black on this side of my face and completely lit on this side of my face, would I? However, if I was in space, that's actually what would happen. If I was out in space and there was nothing on this side of me and light coming from that side, I would simply be lit from on this side of my face, and the rest would be black. And that would be a really simple lighting model to set up. Just say there's nothing affecting the light except a single light source somewhere over there. It lights up my face from this side, so whatever on my face is facing directly that direction will be bright. As I go to the front of my face, it will get darker, and when I'm at this side of my face, it's just completely black. There's nothing there. But in reality, we have this room and light is going all over the place, so we need to take into account more complex things. But let's start with this lighting model that just has that single light, and we're in space, so there's nothing on this side of me, there's nothing for the light to get reflected off of. The only thing that I have is an object that I'm lighting, and kind of where it's facing. So if we just draw a simple image of that, we have a light source here. And we have, let's say we have kind of several polygons that this object is built up of. So what I'm drawing here, let's make this a little bit clearer. What I'm drawing here is different parts of the surface and a vector that tells me in which direction these parts of the surface are facing. So I have this light here. We imagine just the overall effect here. We're going to imagine that this side of this object is more or less going to be brighter lit than this side here. And if we actually look at the vectors here, this normal vector, so I have a normal vector here for this surface, we can see that the normal vector here is pointing more or less towards the light. And that's the face that we're going to imagine has the brightest color, right? Just from experience of looking at things and putting up a lamp on one side and lighting them on things, we're going to imagine that whatever has a surface facing directly towards the light is going to be our brightest lit surface. So how can I make a calculation that somehow represents this? You see that this here, we're going to expect this to be completely black, right? We don't expect any light to have an effect here. What about this one here? It's kind of facing away, so we're going to imagine that's black as well. From here, though, and up until here, we're going to imagine that we have kind of growing levels of color intensity. So it'll be bright here, it'll be black here, in between it'll kind of go towards that. So can you see any calculation that I can do if we simplify this image a bit and say, what I'm interested in is this point here, P. So I have some point here, which is the position of the vertex that I'm drawing. And for that point, I have a normal N. And I have a position for my light. Just call that light position to be absolutely sure what we're looking at here. Is there anything in particular that I can kind of look at here? Are there calculations that I can do? This is an actual point in 3D space, so I have its coordinates. This is an actual point in 3D space. And this is an actual vector. I'll draw this here as well, just simplify it even more and say this is my point P. This is my vector N. This is the position of my light. So if we imagine this intensity, this effect on where the light is in relation to where the surface is facing, we want it to be some kind of function of how directly the light is hitting the surface. So if the light is right here and hitting the surface straight on, we want this to be high. And if it's somewhere over here, or even behind it, we want that to be very low. So what range of numbers would we imagine would be nice for a factor that we just want to be able to say, like, it's no value when it's somewhere around here, and its full value when it's here? Like, what would be a nice value for a number that's no value?
0.
0, okay. What would be a nice value for a number that's something I want to represent as full value?
100.
100 or 100%, or just 1? Okay. So 1 is fine. So if we imagine, okay, I want for this kind of the direction to the light, I want my final value to be 0 here, and actually all the way behind. And I want it to gradually go to 1.0 here for full value, and then gradually go back down here. Again, can we use this position, can we calculate something from this that will make it easier for us to get this value? What can 2 points give me?
Vector.
All right, a vector. So if I go ahead here and say this vector, I'm going to call the vector S. And S is the light position minus my point P. It's a lowercase s. Okay, so I have the vector S here. So what can I now do with this vector S that may give me this intensity value from 0 here to 1 here? Like, when should it be 1? What should the relation between my normal and the vector S be when it's 1? Yeah, parallel. Okay, they should be parallel, but when it starts becoming 0 down here, it should be perpendicular. So we know something that gives us 0 when two vectors are perpendicular. So can we do something like, all right, I want to set up a calculation here and say I have some intensity here, and I want it to be the dot product of n and s. Okay, so that gives me 0 when they're perpendicular. What does it also give me if the light is behind? The light is here, this is the vector s. What does that tell me about the relationship between s and n? Okay, it gives me a negative value. The dot product will give me a negative value because the angle between these vectors is obtuse rather than acute. All right, fair enough. So glättad here means I get a negative value from this. So can I then say I want this intensity to be the max of this and 0? That makes sense? So if it's lower than 0, I'll get 0. I don't want to get a negative value. If I take a negative value and start multiplying that with my colors, I'm going to get weird results. Instead, I'm just going to say if it's a negative value, the light is behind whatever I'm trying to light up. So I get, so instead I'll get 0. What if it's here? Am I going to get an exact 1 from the dot product? Or in which case would I get an exact 1 from the dot product? Can you remember when we were calculating the angle between two vectors? We had a formula that could give us the cosine of the angle between two vectors. And the cosine is 0 when two vectors are perpendicular, and it's 1 when two vectors are parallel. Right? When the angle between two vectors is 0, the angle 0, which is here, gives us a cosine of 1. Okay, but how did we calculate the cosine? The cosine was in just the dot product, or was the dot product?
N dot s then having divided by n dot n, or s dot s?
Or both, actually. Or, well, actually neither. It's the actual length, so we need the square roots as well. So to get the actual cosine, it would be the length of n times the length of s here. Unless, of course, if we want to think about optimization right away, if either n or s or both are unit length to begin with, then we can skip them the normalization. We can skip actually finding the length. But if we don't know, if you can't trust that they're unit length, then yes, we're going to have to take the lengths and we're going to have to divide by them. So it can be a good optimization to make sure that our normals are always unit length. When they come into the shader, then we don't have to normalize the normal. It's harder with the vector S because we're calculating that from the light position and the position. But in some cases, we just have directional light, so we don't have to calculate it. We just say the light is that direction, and then we can make sure that it's unit length. Anyway, so here we have the cosine of the angle between these two vectors. We have a vector that's basically pointing towards the light. We have a vector that's where the surface is facing. If we look at it here, in this case, we have this vector n. The light is facing this direction. We're going to get something that's probably closer to 1 than 0. In this case here, for this vertex, we're going to get something that's very close to being 1, because the normal and the vector s are parallel to each other. However, if we get something that's negative, we simply set up the formula as the maximum of the cosine of the angle, and 0 to make sure that we don't get negative values. And also we don't want to just do the absolute value of them, because then we just get higher intensity on the backside as well. Okay, so what we have here is in fact let's simplify this image again a little bit. Just going to put the image itself here. Say we have, for some point P here, we have the vector S that's pointing towards the light. We have the normal n. And we have this idea that we call diffuse lighting. Diffuse lighting. And we have this factor that we're going to call Lambert. Or we're not going to call it, it's called Lambert because a mathematician and computer graphics expert named Lambert coined this and decided to give it his own name, like so many important researchers. Lambert, equals the maximum of the dot product between these two vectors divided by the length of these vectors. So it's basically the dot product between the normalized vectors, or if lower than 0, then 0. What we now need to take into account is that somewhere in our shader or in our program, we've defined particular colors of the light. So we say not only do we get this intensity based on how directly the light is hitting the object, we also need to say that we have some material diffuse intensity of the surface that we're calculating for, basically the material of the object that we're drawing at this point. So we're going to say our intensity equals the intensity or diffuse intensity of the light times, I'm going to call here the diffuse color of the material, times Lambert. And this gives us the diffuse color factor, or the diffuse part of the color. So we're going to have to do these calculations in the shader and say we need to have this diffuse intensity for the light, which is basically just a red, green, blue color. So the diffuse intensity for the light is the light's color. The diffuse factor of the material is basically the color of the fabric that we're kind of making this object of. Lambert then gives us the intensity of how directly this light is falling on this particular object. And so we have this underlying color, which is the color of the light, multiplied with the color of the material, but then we multiply that with the intensity as well. yeah, which acts as kind of an attenuation factor on that. It can go up to 1, which gives us just this full color, but it never goes above that. And then it can go down to 0 and take it down to complete darkness. Other questions regarding this part of this? So what the diffuse lighting is, it's basically, imagine a light that falls on a completely matte surface. Yes, question?
The surfaces that are partially reflected need to take camera position into consideration.
Okay, the question is if we need to take the camera position into account as well, if we have kind of reflective properties on the material. And the answer is yes. But what we do to simplify this is that we kind of take this diffuse idea, this kind of lighting of a matte surface, where we don't take the camera into account, and we calculate that separately. And we take another part of the light, which we call specular light or specular lighting, specularity, and there we take the camera into account, and we light that. I'm just going to go into that in a second. And then we kind of have a similar factor, but that factor is affected by not only the position of the light and the position of the vertex itself, but also the position of the camera. But to begin with, just to make sure we're understanding what kind of diffuse lighting represents, if we imagine a light falling on a completely matte surface. Imagine this is a surface here. The light may be coming from this direction, and it hits the surface here. And depending on how directly it hits it, the intensity will be high. But I may be looking at it from here with my eye, or I may be looking at it from here. But when it hits the surface, we imagine that it distributes the resulting light, the reflected light, evenly in all directions. We can even imagine, if we look at a matte surface at a microscopic level, let's put our little magnifying glass here. If we take the surface of a matte surface on a microscopic level, we can imagine that it's a rough surface. It's a surface that's all over the place, which means that a light might hit here and it's reflected in this direction. It might hit here and it's reflected in this direction. It might hit here and it's reflected in this direction. So light coming from the same direction, just millimeters apart, will be reflected in different directions, because a matte surface, usually on the microscopic level, is very rough and all over the place and just distributes light uneven, or not evenly, but kind of in all directions. So that's what diffuse lighting means. It doesn't matter where I'm looking at it from. It only matters how directly the light is shining onto it. But when it hits, it's distributed all over the place. So the camera can go all over the place and the intensity will not change. But move the light and the intensity will change. All right, then we can kind of imagine we have a more reflective surface, a more smooth surface. And on the microscopic level, it's just as smooth as it looks to begin with. So in that case, we imagine that the light hits here and it reflects in exactly this direction. And so if my position, or the position of the camera basically, if I'm looking at it from here, I'll see it super bright. But if I'm looking at it from here, this reflection will have no effect. Basically, the diffuse light will go all over the place, and I can look at it from here and I'll see the intensity equally to someone who's positioned here. But for the specular light, for this reflection, I'm imagining there's part of the light that just reflects more strongly exactly around the normal N. So I have this normal here, and there's part of the light that will be the strongest right here, where the light reflected about the normal of that vertex will go directly into the camera, and that'll give me the highest intensity there. Different from the diffuse, where the only factor that affects it is the position of the light. So now let's add the camera here, or add the eye. So I have an eye here looking at this, and I can take another vector and I say, okay, This vector here is the vector v, which is the camera position, or let's call it I position. I position minus the position of the vertex. I'm going to call that the vector v. Now how can we make up a similar factor to the Lambert factor using these vectors here? Like, what am I looking for? So earlier we took the cosine of this angle between S and N. Now we're kind of thinking, wait a minute, if I take a vector that goes from the light and I reflect it around N and get a vector here that we can call R, the reflected vector, how would I get the most intensity now? If R were parallel to what? Okay, if R were parallel to V, that would mean the light is reflecting directly into the camera. I should get the highest intensity there. I should get a full 1 there. Let's imagine for now that we're just going to let it kind of drop off at the same rate as the other. So we're just interested in the cosine. So the cosine of this angle would be kind of what we're looking at. So now the question is, how are we going to put this into calculations? And before we continue, I'm going to tell you, we can figure out how we can put this into calculations, but it'll be fairly expensive. And there's actually something else that we can do cheaper. But to begin with, just to understand the concept, let's look at this. How can I calculate R? R equals just basically the reflection that we've worked with already. So it's the vector S that we're reflecting, so it would be S minus 2 times, was it S dot N divided by N dot N times N, something like that. I imagine at this point, because S is turning this direction, it would be plus here rather than, or this whole thing negative. Doesn't matter. So this is something that we have to do then. A fairly big calculation to calculate this vector R, to then set it up into something like this and say, all right, now our specular intensity level would be the max of 0 and R dot V divided by the length of R times the length of V. Okay, so this is something that would give me this result. But it costs this fairly expensive calculation. So the question is, rather than calculating a vector R here, this kind of intermediate vector with this full calculation, there is a way I can instead do a much cheaper calculation and say, okay, I'm not going to do this actual reflection. Instead, I'm going to change, I'm going to take basically the vector that I'm reflecting, which is S, and the vector V, which, if I get full intensity, then the direction of V would be the same as the direction of the reflected vector, right? So that's kind of the premise I'm going on here. If I were to reflect S around N and hit directly into V, I would get full intensity. So can I somehow kind of change this problem around a bit and say, what is the vector around which I should reflect so that S will hit V exactly? Like I have N here, but instead of actually reflecting around that, can I take, different color, can I make some kind of halfway vector, H, for halfway? can I make a halfway vector H that is between S and V and would be the vector that if I reflected S around it, I would hit into V? How can I calculate a vector that's right between S and V? Particularly if S and V were the same length. So here we're losing a little bit of information because we're going to calculate a vector that isn't actually correct all the time. But it would be correct if they were the same length. And it's close enough that in almost any case in computer graphics, it'll give you a good enough result to be worth how much cheaper it is. So can I just take an average of S and V to get that halfway vector? Does that sound reasonable? I say this is the vector H, and it equals S plus V. Do I need to divide by 2 to get an average vector? If we take two vectors here, and we take an average, it'll be here. So if this is A, this is B, then this is A plus B divided by 2. But this here vector, all the way up here, is simply the vector A plus B. Since the only thing we're interested in is the direction, we can actually skip the division, right? So this would be the average vector of the two. Just skip the division. The division is just a scalar, and the scalar doesn't change the direction. So we're going to go ahead and say the vector H equals S plus B is a lot cheaper than the vector R equals S plus 2 times S dot n divided by n dot n times n. So my halfway vector equals S plus V. And this is what's the word for nulgun again? Approximation. So this is an approximation, seeing as if the vectors are different lengths. I have a vector here, I have a vector here. It's kind of, the halfway vector is halfway between where these vectors went. So we can see that the angle here is smaller than the angle here. So having these vectors unequal lengths will give us a worse halfway vector. If, however, we're going to calculate Lambert anyway, we may have normalized S anyway. So maybe it's not so expensive to normalize both of them to get the halfway vector better. And this is something that you could just experiment with in your shaders. Do I normalize all of them? Do I normalize none of them? What's the effect? What's the kind of trade-off? In some cases, everything looks kind of nice, even though they're not doing it exactly correctly. So sometimes you can skip the normalizations and just trust the lengths of your vectors. In some cases, you have to normalize over the board to not get strange results. Either way, here we have the halfway vector, H, which is an approximation of a vector exactly between S and V. What we have then is we have basically this imagined normal that would give us a perfect reflection. So now if I want to take the angle between that vector and some other vector, what would that be? Like, when would I want to get full intensity? I have my vector n, which is the vector that's the actual facing of the surface. And I have the vector h, which is this approximation of the facing of the surface that would give me full intensity. Does that make sense? So if n lines up with h, then I should probably get full intensity. However, if h is kind of 90 degrees off from n, I should probably get no intensity. So now I'm going to say, with this halfway vector h, between the vector to the light and the vector to the camera, I'm now that's the only thing I'm going to use S and V for here. Because now I'm going to take the halfway vector in n and say, my factor here, which I'm going to call Fong, equals the max of n dot h. So I'm taking the angle between the normal and the halfway vector, the normal and the perfect normal, so to speak. And if they line up, I'll get a 1. I have to divide by their lengths for this to be completely correct. But again, we can experiment with that in our shaders and see what the trade-off is if we skip the normalizations in some places. So if we get a 0, or if we get negative numbers, we're going to end up with 0. If we get positive numbers, we use those numbers. All right, one more thing with the specularity. Let's look at a surface here. And imagine that I have an eye here. I have a light here. So somewhere here I should get full intensity. Whatever vertices I'm drawing in this area, probably get full intensity from specularity, seeing as their normal would directly reflect the light into the eye. But would it be normal for this kind of shine spot? If you look at the whiteboard, you probably see in different locations, because our own location, our own position has an effect on this. You can see these little shine spots, and if you move your head around, they kind of move as well. Like the light reflecting off the whiteboard or off any shiny surface, off the tables as well. You can look at the tables and I see the lights in the ceiling kind of reflecting off of that. Would it be normal for this to be 1 here and 0 somewhere around here, 0.0, and while cosine is not linear, it's kind of an even fall up from 1 to 0. But that makes sense as a shine. Like if you have a metal ball in your hand, you can see this kind of shine spot that hits in one location. It's usually tiny, because a really, really shiny surface will have a very small kind of this reflection point will be really small, because the surface is so shiny, so exact, that only very close to being exactly here will it give high intensity into the eye, and then that intensity will fall off very quickly. The shinier the surface, the more quickly this will fall off. Does that make sense? So we really want this high intensity to be here, and we want it to fall down, well, it falls down to 0 here. We don't want it to fall down from 1 to 0 like this. We want it to fall down much faster. Like go from 1 to 0 super fast and then kind of trail off closer to 0. So how can we change a function that looks something like this to a function that looks something like this? How can we tighten this curve? If you, for instance, look at just regular parabolic curves, what's usually the difference between one that looks like this and that looks like this? All right, especially since we're looking at kind of the values that are happening between 0 and 1, what we can do is we can take this Fung value, which is a value between 0 and 1. We can say if I take Fung and raise it to a power, let's call this power f. What happens to a value that's, let's say, 0.5? If the value f is 1, then we still get a 0.5. If the value of f is 2, 0.5 will turn into 0.25. If the value of f is 3, 0.5 will turn into 0.125. So it's getting smaller and smaller and smaller. However, a value of 1, how will f affect that? Not at all. Yes? No? So okay, the value of 1 will still be full intensity. But as soon as we go a little bit lower than 1, somewhere between 0 and 1, it'll get lower. So 0.9 times 0.9 is 0.81. So even that close to it, as soon as we raise this power, then the fall off will be quicker. And that'll give us a shine spot that's still at the highest intensity right here, but that intensity will fall off quicker. So we add this factor that we call shininess. F is the shininess of a material. So the shininess factor is part of the material, not part of the light. And then we add to here, so this is the diffuse part. We add the intensity, specular intensity, times the specular material of the, or the specular effect of the material. In some cases, like if you look at plastic, then you could use a specular intensity of the material in a white color, whereas the diffuse part is, well, the actual color of whatever you're drawing, and then you can get kind of a plastic effect. It is of a color, but as soon as light shines on it, it kind of just directly reflects that light in whatever color the light is. This times Fong to the power of the shininess. So this is what we add for specularity. So in order to not have this lecture too long, there's one more thing I'd like to add. So these can both be used in our lighting model that happens in outer space, where there's nothing on this side of me, just something that shines onto this side of my face. The camera is somewhere over there. Like this whole side of my face will be more lit than this one, which will be not lit at all. And then there will be kind of a reflective point somewhere here, depending on where the camera is at. And that'll be moving around as the camera itself moves. But as soon as we go into a room like this, then we have all these reflections. We have light that comes from that direction, but then reflects off of that wall and lights the other side of my face. Inside this room, even if we turn off all the lights and only have the light that comes in the window, I'm still lit from all sides, even though I'm lit the most from the side where the light is coming from. So in order to simulate this or approximate this without it being too expensive, we simply add an ambient factor. And we say the ambient factor of the light, so we have here the diffuse light, we have specular part of the light, and then I'm just going to add an intensity level here, that's the ambient part of the light, ambient light. And we don't need any calculations or any vectors or anything, because we're going to say the ambient light is the light that fills the room from all sides. It's the light that bounces off of every single surface, and we've completely lost track of from which direction this comes. It's just all over. So the ambient light will be added to every vertex that we draw, regardless of which way it's facing. So that's what kind of makes this side of my face lit as well, even though we maybe have lights only coming from here. I'm still lighting this side of my face a little bit. But it's not directional, it's just kind of a flat light over everything. And into our formula here, this is simply adding by saying I have the intensity, ambient intensity of the light times the ambient factor of the material times nothing more, just like that. Now, when we start adding this for several lights, this actually becomes something like this. The overall intensity equals the sum from I equals, say, light 0 up to light n. So we have a bunch of lights, we have n lights, and then I have to say the intensity for light number I, diffuse. The material, though, that's just the one material, so we're always just using the diffuse of the material. I'm saying light number I, its specular factor, and then I have light number I, its ambient factor. So with several lights, I have to do this for every light, and I have to sum the entire thing up. What happens here, though, is that we can definitely think of the ambient factor of the light as if you turn on a lamp in one place in a room, there are two things that happen. Things that are close to it or things that it's directly affecting will get brighter on that side. But also, if you try to have a completely dark room and you turn on a single lamp, you'll see the entire room fill with light a little bit. You don't just see this very directional light to one side. The room also gets a little bit of an ambience. So it's normal to think that every light should add a little to the ambience of the room. If you turn on a red light, the ambient light of the entire room will become a little bit redder. Yes?
How do you map out ambience?
So the question is, how do you map out ambience? Do you want to like pre-calculate it to know how much this should affect? In the approximation that these kinds of things usually are in computer graphics, it's just a number that you have to put to it. It's just a decision. At this point, at least, you just decide how much ambience this light is giving. You just set that as a number. Ways to map it out, I haven't really looked at, like ways to actually calculate how much light of this intensity should add to the ambience. Usually you just set numbers to it. However, what I like to do to simplify the ambience in kind of simple graphics programs like we're doing, especially that if you add a lot of lights and each one of them has ambience, just look at an object that's drawn here, the ambience comes from all sides, so everything will be lit up by that. And in the end, if you add a lot of ambience, the actual three-dimensional shape of the object, which is represented by how it's lit, by its shading, will kind of get washed out by all this ambient lighting. So if the ambient lighting gets too strong, everything will kind of be a flat lighting, and your directional lighting, which is the cool 3D lighting, will kind of lose its effect, or it can lose control of it by adding light after light. So what I like to do, and is part of the static OpenGL pipeline, and we'll add into our shaders as part of our programmable shader light model, is to say I'm going to take this sum and I'm going to add to it one more factor, which is the intensity of my global ambience times the material's ambience. And if I use this global ambience, usually I take this part here, the ambient part, and I just skip that. I just take all the lights and say they have zero ambience. Because if I add light after light after light and everything adds a little ambience to the room, the ambience maybe becomes so overpowering that it kind of washes out my 3D light. So instead, unless we're doing a lot of switching on and off lights in our light model, if we just have a set of lights and have an ambience from them, it's nice to just calculate one ambient factor from all of these lights. Calculate or just decide, just experiment and figure out what looks nice, and just leave that there. So a global ambience in a lighting model can simplify using an ambience for all of the lights. Another thing that I like to do to simplify is to say each light just has one color. A light doesn't have a diffuse color and a specular color. The light just has a color. So I'll just have one variable for light color, or light color 1, light color 2, light color 3, or an array of lights that each have their color. And I'll just use the same for diffuse and specularity. The material should have a separate specularity, because that can really change kind of its color under those conditions. Something that reflects a similar light or similar color to its diffuse color will look more metal. Something that reflects white, while its diffuse color is green, it'll look more like plastic. And then you can go and experiment back and forth with that and kind of figure out how we can get these things to work. But metals usually kind of reflect a similar color to their own color, whereas something like plastic and things like that usually just reflect the light unchanged, just reflect white. So for the material, I often say I'm going to use a specular light, but then I'm going to have another color, or a specular color, but then I'm going to have another main color, which is my diffuse color. I'm just going to use that for diffuse. I'm going to use that for ambience as well, onto the global ambience. So a simplified light model might say I'm going to just skip the ambience part of the light altogether. The light just has one color, and that color is used for the light and diffuse, and for the light and specular. Then I'm going to have a color, like a main color for my material. That's going to be used in diffuse, and it's going to be used in ambience, but just multiplied by a single global ambient factor for this particular room or this particular environment. So that simplifies my lighting model again. The specular color for the material, though, that's separate, but that's used multiplied just with the color of the light, which is the same as here. So the light has the same color for diffuse and specularity. The material has the same for diffuse and ambient. a separate one for specular, and the light model just has a single global ambience. That's a nice simplified light model. However, you can set up a light model that has all of these factors, and it'll be that much more flexible. You can do that much more things with it. You can get more realistic effects. But it's also more complicated to use, so you just, for your first assignments in lighting and shaders at least, it's just a trade-off that you're going to have to decide on. Am I going to simplify my light model? Am I going to make it really flexible? How far am I going to go with this? And then you can kind of build on from there. So this is just me writing a simple formula here on the blackboard, or on the whiteboard, and really doesn't give us a hands-on feel for what the lighting does. So please, let's just go ahead and start with lab assignment number 5, or lab exercise 5, and really get these lighting calculations happening in our shaders and truly see kind of what we can do with that. And then we can start experimenting and start playing around with these values. Any questions in the end with this? All right, cool. Let's take a short break and then get going on actual assignments.